Well, in the second video for Module 16, we consider stream discharge, and then a little bit later, stream patterns. So we'll start with stream discharge. What is that? Well, that relates to this question: what determines the amount of water carried by a stream? And in fact, we measure the amount of water carried by a stream and represent it in terms of the stream's discharge. So those statistics are generally kept track of using a measure of the number of cubic feet per second or cubic meters per second that pass by a location in the stream within 1 second time, so every second. So here's an example of 1 cubic foot of water, 1 by 1 by 1, passing by a location. And if we want to compute discharge in cubic feet per second, we can take the width of the stream times the depth of the stream and multiply that times the velocity, or how quickly the water is moving in the stream. Now, something I want to point out in this diagram, you see these red vectors here. Within the stream, the water doesn't generally travel at the same speed in every part of the channel. So across the channel, the speed of the water is generally the fastest in the center of the stream at the top. So we see this cross-section here. Again, the water is moving at the fastest at the center of the stream, near the top, near the surface. And it's slowing down a little bit down near the stream's bed because of the frictional effect of the bed, but also the frictional effect of the sides of the stream here. To show you how this is actually, how we can measure the speed of water moving in a stream, we do so using a cross-section of the stream, and we can measure what the speed is and sort of average those speeds for different places within the stream channel. So here in this photo, there's some students who are doing this. They're using this thing that looks a lot like, I guess it looks like a propeller. We actually call it an impeller, and it measures the number of rotations. So you can hold this thing out. You see the counter right here will measure the number of rotations, and we can use a table to figure out a table of figures to figure out what the speed is based on the number of rotations over a period of time. Another way we can measure stream discharge in an easier way, I suppose, over a long period of time is using a gauging station. This is a gauging station. You see these along a lot of bigger rivers and streams. They have something that connects, like an intakes that connect with the stream, or these can also be used for lakes, with floats that go up and down, and recording equipment, and then telemetry, satellite telemetry that allows the data to be sent to a remote location. And this is important to keep track of stream discharge because it might have an influence on the amount of water you release from a dam. For example, with snowmelt or spring rains, you might want to make room for water that would be flowing into a reservoir. So you need to release some water. So gauging stations are very important and are generally in the U.S. operated by the U.S. Geological Survey. Here's a sort of a plot of discharge for one river. This is the Grant River over a 365-day calendar, and you can see some high discharge events. That would be probably following spring rains and snowmelt, things like that. Probably rains in this case, because you see a big increase right around day 140 to 145 during the 365-day calendar. So there's probably some type of rainfall event at that time. Stream discharge can also be represented on a chart where we exaggerate what's going on. So let me show you a couple of examples of some stream beds here, and I want you to look at two things. Look at the where the surface of the water is relative to other places that I'll show you. The number CFS refers to cubic feet per second, so that's stream discharge represented in cubic feet per second. And then look how deep the channel cuts down into the sediment. So again, this is 10 times vertical exaggeration, but in this particular river on September 9th, it was carrying 635 cubic feet per second. It started to rise. So just a few days later, probably because of a rainfall event, it was nearly 10 times or over 10 times what it was on September 9th. So you see that the level has risen of the water. It hasn't really pushed downward very much, but the level has risen. And then we look at about a month later, and it's carrying nearly 10 times what it was in September 15th. So October 14th, 59,000 cubic feet per second. So two things have happened. That red line shows you that the water level has risen, but the stream has also cut down into alluvium. So the bed has been scoured, meaning material has been removed to make the channel actually deeper. So those are two things that happen as the stream increased in discharge. So when we see a falling stage, so now the water level has fallen. We're back down to about 18,000 cubic feet per second, which is still a considerable amount. But notice it's not dug as deep down into the alluvium now. The bed has been filled. Okay, a little bit about stream channel patterns. In Oklahoma, where I live, and many of you do as well, we have we have actually two different types of stream channel patterns that I wanted to mention. In the eastern part of the state, with rivers like the Illinois River, a real famous river for canoeing and floating, we have a meandering stream channel. So a meandering stream channel, I'm sort of showing the cross section here from the side, and then also from the side right here, if you look at the profile of that of a meandering channel. But it's where you have a single channel. You see in this example, surrounded by vegetation that sort of meanders around just within a single channel. This particular type of stream, as I say on the slide, fine sediments, constant flow, and heavy vegetation around it. We also have the other type of stream channel in the drier western parts of Oklahoma called the braided stream channel. So what makes this different? It's not a single channel. It's a whole bunch of smaller, what are called distributaries that break off, rejoin, etc. There's a steeper profile typically, so these are a little steeper and steeper terrain, I guess you could say. So we have both types of streams in Oklahoma. And these braided stream channels are associated with coarser sediments, variable flow, meaning sometimes the water level is a little bit higher much higher than others, sometimes they look almost dry, and sparse vegetation. Let's talk a little bit about stream systems. Stream systems are sort of networks of streams, if you will. The land area, and these are streams viewed from above. So these are a number of streams that all flow here down into a larger stream. So this would be kind of a top view, what we're seeing right here. So the land area where water drains and supports a particular stream is called a drainage basin. And maybe you've heard this term. So the drainage basin, I've got one blinking right here for this river. So ultimately, water or rain that falls anywhere inside this blinking dashed line would end up in one of these streams if it travels in overland flow, and then eventually into the larger stream down here at the bottom of the slide. So that's a drainage basin. We see the drainage basin for a neighboring stream here that I don't have it blinking, but this neighboring stream to the right. So the land area is called the drainage basin. The drainage divide, I've got it blinking red here. It's the interfluve. Remember that term interfluve from a previous video? That's a high point on the landscape. So if the low points down in the valleys here are the stream bottoms, the high point, that sort of ridge or that higher elevation that separates drainage basins would be represented by the red line. So drainage divide, and we're going to talk about a special type of drainage divide that defines very large drainage basins, one that's called the continental divide. We'll talk about that in just a minute. Maybe you've heard of that. And then the drainage net is the actual network of streams that make up and sort of all come together to flow into a larger stream. That the example here being flowing at the bottom of this slide. So that's drainage net, or the network of streams. Here's another graphic that helps you to see the interfluve, the high point, or drainage divide, right here in the center of this graphic. And here we have drainage basin A, drainage basin B. So a drop of water falling over on to the left would end up in drainage basin A, and to the right, drainage basin B. So you get the idea. Another view, this is a satellite view of a drainage basin. This one's an actual photograph. This one's near Farmington, New Mexico. But you can see all of the small tributary streams that flow into the bigger ones, even some of the just gullies and things that are the very beginnings of streams. But we see this red line representing the drainage basin for the river that's shown down here in the lower right-hand side of the slide. Sometimes these drainage basins are really big, like in the case of the Colorado River. Colorado River actually has an upper drainage basin, Colorado River coming from Colorado. It flows here through starts in this part of Colorado in the Rocky Mountains, and then flows through Utah, here through Lake Powell, eventually through the Grand Canyon, and then It's sort of a trickle when it actually reaches the Gulf of California because so many entities use this water, like the city of Los Angeles and a lot of agriculture in Southern California. But this is the Colorado River drainage basin, so pretty big. The drainage basin for the Mississippi River is even bigger. So, of course, we know that the Mississippi River drainage basin was used to define the Louisiana Purchase. If you know your U.S. history, an important piece of land acquired by the U.S. Here's these signs that you see up on the top of interfluves, like when you're coming up a pass and sort of going over a mountain pass. Quite often, you'll see these brown signs that identify the Continental Divide, with water falling on one side of the sign draining into the Atlantic Ocean, and any precipitation that happens over on the right-hand side of the sign draining into the Pacific Ocean. These continental divides represent very large drainage basins. Where rivers come together, we call it a confluence. What's sort of interesting, a little side kind of fun story about the Colorado River, where the Colorado River comes together with the Green River, and that actually happens, the confluence is in Canyonlands National Park. The naming conventions that have been used for years for rivers, we always name a river where two come together for the bigger river. So whichever, if one river is bigger than the other, we always use the name of the bigger river downstream of the confluence. But that didn't happen in the case of the Colorado and Green. Somebody made a mistake, and we ended up calling the river downstream of the Colorado Green confluence the Colorado River instead of the Green, and the Green was the bigger river in terms of flow. So it's just a little bit of a kind of an accident there. Here in this upper right-hand view, you see two rivers coming together. One's pretty turbid, has a lot of sediment in it, carried by suspended load, and another one that is just carrying, is supporting mostly cleaner-looking water that's probably dominated by bed flow. Okay, I also wanted to mention something called stream order. Stream order has to do with the number of tributaries that flow into a stream. So if there are no tributaries flowing into a stream, we give a stream, we assign it a 1 on the stream order system. If there are if two ones come together, if two streams that have the number 1 come together, downstream of the confluence, we call it a 2, so it goes up 1 number. Now, if a 2 and a 3 come together, it's still a 3 downstream of that confluence. We always use the larger number. So here's sort of how that system works. Here are some first order streams, and I have a picture over on the left-hand side of the screen. You can see what a first order stream might look like. They're not very big. So we have these first order streams, and then this might be a second order stream. So again, when two first order streams come together, it becomes a second order stream. Now, notice that when this first order joins this second order, it's still a second order stream downstream of that location. So it's only when you have two numbers that are the same that you go up 1 number for the stream. So if two twos come together, it's a 3 downstream of that location. So here's some 3s on our diagram. So you can see 3s are a little bigger. And then finally we get to fourth order stream here at the bottom. This is in the Merced Wild and Scenic River System. Now, sometimes these streams can be really large. So some of the biggest streams, just to give you an idea of what their order is, you've heard of the Ohio River. It's a really big one. It's an 8th order stream. The Mississippi is considered a 10th order stream, and the biggest river on the planet in terms of the water it carries, the Amazon River, is a 12th order stream. So that's a really big stream. But just in terms of numbers, first to third order streams, those are considered headwater streams. 80% of all streams. Medium streams are 4th through 6th order, and anything bigger than a 7 is a river, something really big. And I'm showing here 2 rivers as they come together. This is the city of Pittsburgh right here, 2 rivers coming together. And this is an oddball situation, the Monongahela and the Allegheny rivers coming together. For some reason, downstream of that location, they call it the Ohio River. So it really ought to have one of those 2 names, but they didn't choose to do that. They decided to call it the Ohio River downstream of that confluence. Okay, a little bit about permanence of flow. So rivers and streams that flow through humid areas, where the streams and rivers that are flowing all the time, are called perennial streams. So a stream that doesn't dry out and have a dry bed during some portion of the year, called a perennial stream. And streams that flow only during a portion of the year are called intermittent streams. So intermittent streams, I'm showing the blue line that you see in topographic maps for perennial, and this blue line broken by 2 dots representing intermittent streams. I also wanted to draw a distinction in terms of the stream sort of patterns that, the configuration that different streams take. And I wanted to mention consequent streams. Consequent streams are streams that just basically the direction of the stream just flows with the lay of the land, just follows the contours of the land and flows from, just being responding to the water's responding to gravity, just flowing from higher elevations to lower elevations, not really influenced at all about what the stream or river is flowing over. So the stream direction just follows the topography. So these streams look kind of like, the branches on a tree, if you will, consequent streams. There's another example of what a consequent stream looks like. It isn't really influenced by the underlying geology. A subsequent stream is a little bit different. What happens with the subsequent stream is the stream sort of works its way down through the layers of geology, if you will, through the rock that it's cutting through. It may follow joints and fractures and weaknesses in the rock, and it may take on some pretty interesting angles. So you have these kind of dogleg turns here, or dogleg to the left here where I'm pointing. That's characteristic of a subsequent stream, a stream that is influenced by the underlying geology. And here's an example of a subsequent stream. Again, you can sort of see how these rocks here are kind of controlling, to some extent, the direction of the stream. Let's walk through some stream patterns, and as I talk about these, think about whether each one of these is a consequent or a subsequent. So we'll start with dendritic. What do you think about dendritic? Is it consequent or subsequent? Remember, consequent only influenced by the lay of the land, the topography, and subsequent would be something that's definitely influenced by underlying geology. So if you said consequent, you're correct for the dendritic pattern. The trellis, yeah, that's a subsequent. We've got something going on there that's controlling the direction, some influence from the rock that these streams are flowing across that's influencing their direction. So radial, this is typical of hills or I should say mountains like volcanoes. So this is probably in the category of consequent. So again, just flowing, the water just responding to gravity, just flowing following the path of least resistance across the topography, and then this parallel drainage pattern is definitely a subsequent one. One other sort of category that I wanted to mention, one other special attribute that streams have, there are some streams that have been around a long time, and they actually predate mountains that sort of formed around them. And a good example is Delaware Water Gap. So Delaware Water Gap it's actually a national park site that you can visit, and it's a pretty neat place to go. But the river that you see right there, the Delaware River, has been there longer than the mountains. So imagine this: the Delaware River continued just to cut and just sort of maintain its flow. And I have this animation here on the right. Watch this animation. And as these mountains rose, the Delaware River just kind of stayed there and just kept cutting down as the mountains rose. So even though the surface has been uplifted, the river is still there in the same place. Another example of that is how you can see these sort of things in drier states. This is Gooseneck State Park, and here the Colorado River just continues to cut down as the land surface is pushed up. I mentioned this a little bit, I think, in a previous video where I mentioned it's just sort of like a knife cutting through butter. That's kind of what's happening here. As the land surface pushes up, the river continues to cut down, and it forms these really unusual meanders, which are really quite amazing. Okay, a little bit about valley deepening and valley widening. So valleys over time can get deeper and wider, and we'll take a look at, we'll start with valley deepening. The characteristic way that rivers cut down is in V-shaped valleys. Most of the erosive effectiveness is right there at the bottom of the valley. So you see some erosion and mass wasting that happens along the sides of the valley, but really the focus of erosion is right there where the stream is. Now, occasionally, as rivers run across rock that might be more resistant, you can end up with something that looks like this. This is called a nick point. So this is where a river is sort of crossing over some really hard geology, some harder rock that may be more resistant to erosion, and it creates this rapids. So rapids is one example of a nick point. So a nick point just being a place where the water flows over some type of really hard rock or irregularity in its journey downstream. So nick point would be one. Another example besides rapids would be a waterfall. So here we see both. In this diagram that I created, you see this sort of a side view. Here the water's flowing over this hard rock, and it ends up falling as a waterfall down in the plunge pool here. And over time, the water, as it continues to fall, will undermine and sort of remove material below this hard rock, and eventually you might have the collapse of the overhanging hard rock. And this is a big reason when rivers, when waterfalls develop, they continue to push upstream. So they undermine the harder rock that they flow over, and they continue to push upstream. Sort of an interesting thing about this particular type of nick point. The other nick point shown here are these harder rocks. I'm sort of showing in this example what we're seeing right here with the rapids area, where hard rock kind of sticks up a little bit and creates a rapids area. Now, one example of a pretty amazing waterfall, one that I had a chance to visit, is right on the border between Zimbabwe and Zambia, two countries in sort of the southern portion of Africa. And this is Victoria Falls, a really amazing place to go. And if you can imagine, over time, this whole sort of curtain of this waterfall has pushed back. And I'll show you in just a moment. I'll show you some sort of a satellite or a aerial photograph of how this curtain has pushed back, and the waterfall location has actually changed over time. And here it is right here. If you can imagine, this is the bridge over Victoria Falls, or near Victoria Falls, that forms the border crossing between those two countries, Zimbabwe and Zambia. And here you see over in this, to the upper left-hand corner, you see the actual falls. But the falls were here, where the bridge is, and the falls were also over here. So these channels here represent different places where the falls were at various points in time, and there'll certainly be another place farther upstream as this waterfall continues to migrate upstream. And here you see an aerial view, and you can sort of see this is the Zambezi River right here, which is flowing. It's a kind of a braided river here, and then it flows over Victoria Falls. It's really quite wide. It's over a mile wide, and then it just forms in one channel as it goes through these areas where the falls existed at one time. Another pretty famous waterfall that represents a nick point is Niagara Falls, and maybe you've had a chance to see Niagara Falls on the border between the U.S. and Canada. A pretty impressive place, and I wanted to show you when Niagara Falls was first sort of, I guess you could say, discovered. I mean, it wasn't really discovered, but it was made known to Europeans in the late 1600s. This is the location of where Niagara Falls was located, what is today called Horseshoe Falls, or that part of Niagara Falls. And we plotted each of these circles represents another location for Horseshoe Falls as this nick point has continued to migrate upstream. So this whole thing migrates upstream over time. Okay, a little bit about valley widening. We talked about valley deepening, but a little bit about valley widening. One of the things that I've previously mentioned is that the velocity of water moving in a stream channel is not the same all the way across the stream. And I mentioned that it's usually the fastest in the center, except when you have a stream that curves. When that happens, just like when you're driving a car and you're sort of thrown to the outside of a curve, driving a car, same sort of thing happens with water. And as a faster moving water comes around this curve, it will erode more on this, what we call this cut bank. So this is a cut bank over here where it says erosion. And then as it swings around, it's actually on the inside of the curve, the water isn't flowing as quickly, and that's where you have deposition. So that's where some sand, silt, other materials carried by the river, alluvium, will build up. So you have material being removed on one side and deposited on the inside of these curves. And here's another cut bank over here and another point bar area of deposition. So wherever the water is moving slowly on the inside of the curve, you see deposition, sand kind of being left behind, and where it's moving more quickly, you see erosion take place. And here's kind of a view of that from an aerial photograph and a little animation. These green areas show the areas of deposition over time. Now, one thing I wanted to mention, I like to say a few things about rivers as borders. So rivers are, back when North America was being settled, rivers were really pretty good pretty good as borders. I mean, they're pretty identifiable. You can, it's not hard to, you can't get in too much of an argument over where the Mississippi River is or various types of rivers. So rivers in the early development of our country were excellent borders, and they continue to be used as borders today. But one problem with rivers is they do move around a little bit. And, you can see if you can name some of these rivers that I've identified here. But we'll move on and talk about rivers as borders. So rivers were used as borders back, for example, when the Louisiana Purchase was made by the U.S. from France. So we purchased this area called the Louisiana Purchase from France, and we defined part of the we basically defined the purchase based on the watershed area of the Mississippi River. So this is the Mississippi River watershed, and we have over on one side of the border here the actual Mississippi River. Just to show you how much rivers move, this is the Mississippi River, and I've sort of plotted it over time. Beginning in 1955, I know that's sort of an arbitrary choice for a particular time period, but just so you can see how much the Mississippi River has moved, and we'll put some red lines on there you can see. So the red lines represent this island here in the middle of the Mississippi. I just picked this one, and the banks of the Mississippi in 1955. So if we fast forward and we keep the lines in the same place, but we show on another topographic map where the Mississippi River is, that island has moved. Okay, something else is formed just a little bit to the north of that island, and of course the banks of the Mississippi are a little bit different. Now we're keeping the 1955 location here in 1965. You can see the change between 1955 and 1965, 10 years of change, 1973, and then finally 1986. So here we have a couple of different islands. So you can see the rivers will move around considerably, and that's a place that's where the Mississippi comes or passes Memphis. That's a place where there's probably less change than other parts of the Mississippi. There's some motivation to try to keep the Mississippi from moving around too much because you have to move the location of bridges and there are other reasons. But just to show you some other changes in the Mississippi, when the original boundary between Louisiana and Mississippi was identified, it was the Mississippi flowed along this red line. So today in the Mississippi, it looks very different. And what's happened is it sort of left some places, for example, this whole area of Mississippi is trapped on the other side of the river. So it's actually part of Mississippi, but it's located over here on the west side of the river rather than on the east side, this area south of Vicksburg, Mississippi. And one of the best known places where this sort of thing has happened and produced an unusual situation is this place called Kentucky Bend, which is Fulton County, Kentucky, and it's an entire county of Kentucky that's separated from Kentucky by the state of Missouri. So you'd have to actually go if you were traveling here from this county south of New Madrid. You'd have to cross over the Mississippi, go through Missouri, and then cross the Mississippi again to get to Kentucky. We call this an exclave. So an exclave is something that's not attached. And back in 1820, the population of Fulton County was only 2 people, but it rose pretty considerably through the late 1800s. The population has declined as you get into 2000, 2010, but you can see some people were really affected by this. And here's a aerial photograph so you can sort of see not a huge number of people living in this county, but still, I mean, the 2010 census, 18 people living in this county. So not a really big county in terms of population, but kind of an interesting case study. How about this one? What treaty defined the border between Oklahoma and Texas? Do you know? So there was a treaty between 2 countries. The other question I've got on here is, where's the boundary between Oklahoma and Texas? So we know it has something to do with the river, maybe the Red River, but let's try to be exact. So let's try to address those 2 questions. Well, the first question, the treaty was the Adams-Onis Treaty. It was made between Spain and the U.S. at a time when Mexico was there were a lot of rumblings of Mexico becoming independent. But what they did is they identified the Red River as being the boundary point or the boundary line between the U.S., in this case the Missouri Territory, and Spain, which very shortly after this happened became Mexico. But let's talk about exactly where that boundary is located. So here's a view of the Red River separating Texas and Oklahoma. So where would you expect it to be? Well, probably most people would say in the middle of the river, right? Well, that wouldn't be correct. The actual boundary is on the south side of the river, the south vegetative line on the river. So some point of pride, I guess we Oklahomans can hold over the heads of our Texas friends. So, okay, we'll move on to another question. Is it possible to stop rivers from changing course? Well, that's hard to do because rivers are pretty powerful. Some places, like this river in the Netherlands, they've built groins out into the river to sort of slow down the velocity of water, because we know faster moving water is going to erode and sort of facilitate the river from changing course. Of course, here we have a bridge going across this river. You probably don't want to have to change the location of that bridge to, put in a new bridge or make it longer. So it's really inconvenient if the river moves around. So these groins are an attempt to slow down the velocity of the moving water and keep this particular river in its present channel. Some other things you can do: you can add riprap. This is just rock that's been piled up to try to protect the river or preserve the river channel. You can also put in things like this. These are concrete riprap, and or rock baskets to try to stabilize the riverbank. And if you don't have that, and you have old cars, well, use the old cars for that purpose. So, so the idea here is to, again, slow down the moving water, but also to stabilize the bank a little bit. And then, of course, it's really inconvenient if it's an international border. You don't really want it moving around a lot. And so some international borders, this is the Rio Grande. We don't say Rio Grande River, right, because that means you'd be saying river twice. So we just say Rio Grande. Between Texas and Mexico, they've channelized it. They've actually poured concrete to keep the river in just one place. So it's super inconvenient if a river forms an international boundary and it's moving around, because it creates a lot of problems, a lot of international problems.